Morning, everyone. For those who got up this morning and still pitched despite last night's activities, you're absolute champions. Was it worth it? Hell yeah. Hell yeah. Anyways, let's get to the topic at hand. I'm excited to take you on a journey into the world of quantum computing, specifically focusing on the fundamental building block that makes it all possible, the qubit. But first, I think some introductions are underway. Hi, I'm Bryce, and I work for MServe. It's an internal department in BBD, and we mainly deal with AWS. In today's talk, we'll begin with what a qubit is. We'll then discuss the practical applications and challenges of a qubit, how they are physically realized in the real world, and we'll also look into how quantum gates and circuits operate. And we'll conclude with a summary of the key points mentioned. Whether you come from an electrical engineering background or have found yourself here by some stroke of luck, I think we all know what a bit is. It's the fundamental unit of digital information represented by the zeros and ones. This is physically manifested as an electrical pulse of high or low voltage, occurring many times per second. However, in the quantum realm, where we deal with incredibly small entities like atoms and electrons, things work a little differently. Classical physics breaks down, and the laws we know no longer apply. Quantum mechanics is inherently probabilistic, and precise prediction is impossible. Even the act of observing something changes its behavior, as if quantum physics gets stage fright. So what exactly is a qubit? Without going into the mathematical definition, it's the fundamental unit of information in quantum computing. But unlike classical bits we've mentioned, which are strictly 0 and 1, a qubit exists in a superposition of both states simultaneously. It's partially 0, partially 1, which we call spin up and spin down, by the way, and it's also both at the same time. Now, why is this so useful? Well, when a qubit is entangled, phenomena where the state of one qubit is directly related to the state of another, regardless of the distance between them. This can be millions and millions of kilometers. Quantum computers can manipulate multiple qubits in the same operation. This means that if a classical computer can perform one calculation on n bits at a time, and a quantum computer can represent all possible combinations of those n bits, so that's going to be 2 to the power of n at once, and operate on all of them because of superposition and entanglement, then a 20 qubit quantum computer can process 2 to the power of 20 operations. That's over 1 million operations in comparison to the one operation performed by a classical computer. 1 million versus 1. Now, if we just scale this to 300 qubits, you can represent more states than there are particles in the observable universe. Sounds powerful, right? Unfortunately, there won't be any qubit graphic cards for your new Minecraft mod, or for those who are passionate about your Rust applications. Why? Well, even though the math says it's possible, physically building these things is incredibly difficult. Qubits cannot be simulated perfectly. They are susceptible to noise, require redundancy, and are often quite difficult to scale. However, the biggest issue is due to a peculiar property of quantum mechanics, which makes it rather difficult to extract an answer. Remember the 20 qubit example previously mentioned? All the answers are 2 to the power of 20 calculations, which is 1 million, is embedded in a superposition of states. So they're all there in those 20 qubits. But as soon as we observe just one of them, the superposition collapses and all other answers are lost. They're gone. We only know one of them. This is not due to a physical disturbance, like I am projecting my voice to you right now, but rather an unexplainable part of how quantum systems operate. So what now? Well, we can create specific quantum algorithms that make use of interference, where the incorrect answers cancel out and the correct answers are amplified, making them more likely to be observed upon measurement. However, these quantum algorithms require certain properties to be met. For instance, certain operations can only be processed by a quantum computer if they are periodic. And unfortunately for the world of encryption, RSA encryption is one such problem. That's a big oof. But you may ask that by the time we crack RSA, right, which is going to be 10 to 15 years from now, right, wouldn't we have already moved on to another encryption algorithm? Well, that might be true, but vast amounts of information being transmitted across the internet today will still be valuable 10 to 15 years from now. This can be patents, schematics, classified files, incriminating conversations with your lawyer, literally anything, right? This procedure is known as store now and decrypt later, or SNDL. Anyone who has downloaded your encrypted data is not going to understand it now, but if it's worth something to them 10 to 15 years from now, well, then they can unencrypt it and your data is exposed. So essentially, it's already too late. This is why a lot of governments right now are promoting the use of the new encryption algorithms. I think they use lattices in matrices. So now we know what a qubit is and how it benefits quantum computing for certain problems, right? But how do we physically represent qubits in the real world? There are three popular methods. There are neutral atoms, trapped ions, and superconducting circuits, which is one of the most popular. In superconducting circuits, quantum information is stored as the direction of an electric current in a small superconducting loop. By applying microwave pulses, we can manipulate the state of the qubit, allowing it to exist in a superposition of the current flowing clockwise and counterclockwise simultaneously. Entanglement is typically achieved using a component called a coupler. Both Google's 53-qubit and IBM's 433-bit quantum computers utilize these circuits. Right? I think a little flex by IBM over there. Now, in order to perform logical operations on qubits, we first need to understand how classical computers perform their operations. Right? Traditional computers make use of logic gates. Common examples include the AND or NOT gates. Together, these gates become a universal gate set, and any computational problem can be solved via a combination of these universal gate sets. We need something similar to solve quantum problems. In quantum computing, quantum circuits are composed of three main types of gates: single qubit gates, 2-qubit gates, and measurement gates. Specific variations include the Pauli X gate, the Hadamard gate, and together these gates can become a universal gate set, essentially solving the quantum algorithms. In summary, qubits leverage the principles of superposition and entanglement to store and process a vast amount of information simultaneously. This allows quantum computers to tackle complex problems more efficiently. But there's a catch. Although qubits can exist in a combination of states when they are measured, they must fall into one of their base states, and all other information is lost. This is why quantum computers are not a replacement for classical computers. They do, however, have the potential to revolutionize cryptography, material science, optimization, but only for specific problems. Thank you.